This is Learning Assessment Problem 1112. And the problem-solving strategy here is that of three-phase balanced AC power circuits. In this problem, we are referred to the Learning Assessment Problem 11.3 and asked to determine the real and reactive power and the complex power at both the source and load ends of the circuit. If we look at the statement of problem 11.3, we see that we have a Y-connected load connected to a Y-connected source, and the transmission line joining the two has an impedance of 1 plus J1 ohms per phase, and we were given the load impedance in that problem of 8 plus J3 ohms. We were given the load voltage as 104.02 at an angle of 26.6 degrees volts for the A phase, and we were asked in that problem to determine the phase voltages at the source. One result which we'll use in the solution for the current problem is that the A phase voltage was 120 volts at an angle of 30 degrees. So here we sketch the equivalent circuit for the A phase. We have the voltage source VAN. We have the line current I sub AA. The impedance of the line is indicated, as well as the load impedance. We have the neutral line at the bottom of the circuit, and the voltage appearing across the load is V sub capital AN. We were told in the problem statement that V capital AN is equal to 104.02 at an angle of 26.6 degrees volts. We have the load impedance Z sub L is equal to 8 plus J3 ohms, which is equal in polar form to 8.544 at an angle of 20.56 degrees ohms. Then we'll use the AC Ohm's law to solve for the line current I sub AA is equal to this load voltage V sub AN divided by the load impedance, or I sub AA is equal to 104.02 at an angle of 26.6 degrees volts divided by the 8.544 at an angle of 20.56 degrees ohms for the load impedance, and this is equal to 12.175 at an angle of 6.04 degrees amperes RMS. So now we can proceed to solve for the power, real and reactive, associated with the load end of this circuit. The load power P sub L is equal to the magnitude of the V sub capital AN times the magnitude of the line current I sub AA times the cosine of the difference in angles between the load voltage and the line current. This will be equal to, here we have the 104.02 volts times 12.175 amperes, and then the cosine of the difference between 26.6 degrees for the voltage associated with the load and the 6.04 degrees associated with the line current, or P sub L is equal to 1185.81 watts. Similarly, we can calculate the quadrature or reactive power associated with the load. Q sub L will equal the magnitude of the voltage times the magnitude of the current times the sine of the phase angle difference, which is 20.56 degrees. And Q sub L at the load end is equal to 444.68 bars. At the source end of the circuit, we can calculate the source power as S sub S is equal to minus VAN times this line current I sub AA conjugate. The minus sign here comes about from looking at the original circuit sketch. We have that the current I sub AA is leaving the positive terminal of the V sub AN source, so in the passive sign convention sense, we'll have a minus sign for the calculation of the power absorbed. Thus, S sub S is equal to the minus sign we can write as 1 at an angle of 180 degrees, and then we have that times the voltage, which was given as 120 at an angle of 30 degrees volts. That was a solution from the Learning Assessment Problem 11.3, and then this current, which is Here there's a negative angle associated with the current phase angle because of that complex conjugate operation. Or we will have, when we do the mathematics here, that S sub S is equal to 1461 at an angle of 203.96 degrees volt amperes. So that's the power absorbed at the source end of the circuit. Now we can calculate the real power and the quadrature power at the source end. For the source power, we will have that equal to the magnitude of that complex power, which we just calculated, S sub S cosine of that angle of 203.96 degrees. And this will equal minus 1335.65. Those will be watts for the power. And then similarly, we'll calculate the quadrature or reactive power as this magnitude again times the sine of the 203.96 degrees. And that's equal to minus 593.55 volt amperes reactive. So then we can write the complex powers as, so here we have the load complex power, 1185.81 watts for the real part and 444.68 bars for the reactive part. And that's absorbed power, both real and imaginary. At the source end, we have minus 1335.65 watts for the real part and minus J 593.55 for the imaginary part, and those would be volt amperes reactive or VARs. Both of those are absorbed quantities. Now we can take the power at the source end and define an S sub S primed equal to the negative of the complex power, which would be the supplied power, and S sub S primed would equal 1335.65 watts plus J 593.55 for the complex part, VARs, and those would be supplied powers that the source supplies.